we're going right to the bedrock.
Yeah.
How we understand the universe.
Yeah.
And believe it or not, it hinges on a number. It's so tiny, it's almost impossible to fathom the Planck constant, or H.
That's right. And this isn't some, dusty relic from a physics textbook.
Yeah.
This constant, incredibly small as it is, it underpins the behavior of the entire quantum realm.
Right, the world of atoms and particles.
Exactly. The world of atoms and the particles within them. It's where things get, well, weird in the most fascinating way.
Absolutely. Think of it like this. If the universe was built with, say, fundamental ingredients, like atoms, the Planck constant would be the recipe. It dictates how those ingredients behave at their most basic level.
That's a good way to put it.
So our mission today, diving deep into some compelling explanations of H and this perplexing principle of wave-particle duality, is to reveal why this seemingly insignificant number is actually a cosmic game-changer, packed with aha moments about the true nature of reality at the smallest scales.
Should be fun.
Okay, so let's start right at the heart of it. What exactly is the Planck constant?
Okay, so at its core, the Planck constant, symbolized by H, it's a fundamental constant in quantum mechanics.
Right.
Historically, its first big role was defining the relationship between a photon's energy that's a single packet of light and its frequency.
Okay, frequency, like how fast it wobbles.
Exactly, how rapidly its wave oscillates. The equation is, well, it's elegantly simple. Energy E equals the Planck constant H times the frequency, E high. So this incredibly simple equation, almost like a secret code, it connects something we see as a wavelight with a frequency to something we think of as a packet of energy, a photon.
That's it.
It's the first hint that our classical intuition, our everyday view of the universe, is about to be turned on its head. Precisely. And its significance extends far beyond just light. The Planck constant represents the fundamental unit of, let's call it granularity.
Granularity, like pixels on a screen.
Sort of, yeah. In energy, momentum, and what physicists call action at the atomic and subatomic levels, it tells us these quantities aren't infinitely smooth and continuous.
Okay.
They come in fundamental, indivisible packets. Think of action in a physics sense as maybe a kind of cost associated with something happening over time or space.
A cost. Interesting.
Yeah, and the Planck constant then tells us that this cost at the quantum level isn't continuous. It comes in fundamental units.
That's fascinating, this idea of a fundamental unit of action.
Yeah.
So this H didn't just appear out of thin air, right? There must have been a problem.
Oh, absolutely not. Its origin lies in a major crisis in physics. This was around the turn of the 20th century, the Blackbody irradiation problem.
Ah, yes. Blackbody radiation.
Imagine an ideal object that absorbs all light, then emits it back when heated a black body. Classical physics made a prediction, and it was wild.
What did it predict?
That such an object should emit an infinite amount of energy at high frequencies. It became known as the ultraviolet catastrophe.
Infinite energy. Yeah, obviously, when scientists looked at real black bodies, that didn't happen.
Not even close.
Right, an infinite amount of energy. That definitely doesn't sound right. So how did Planck make sense of this mess?
Well, in 1900, Max Planck took a radical leap, a huge leap.
Okay.
To solve this catastrophe, he proposed that energy wasn't emitted or absorbed continuously, but in discrete packets, these quanta.
Quanta. Little packets.
Little packets. He theorized that the energy of each of these energy packets of electromagnetic radiation was directly proportional to its frequency. And the constant of proportionality was this new constant H. His formula, E high, it perfectly matched the experimental data for blackbody radiation. Just spot on.
Wow. So this simple equation was the key, unlocking this huge puzzle.
Yeah.
And it brought with it this revolutionary concept of quantized energy. But I remember reading that Planck himself was initially quite hesitant about whether these quanta were, real.
That's a very insightful point. Yeah. Initially, Planck viewed his quantization idea more as a mathematical trick.
Just a trick.
Yeah, a convenient way to get the right answer. He wasn't fully convinced that energy was actually fundamentally lumpy. But the implications of his work proved to be far more profound than just a clever calculation. It laid the groundwork for everything that came next. Quantum mechanics.
The whole field. Okay, so what's the actual value of this incredibly fundamental constant? It must be ridiculously small if we don't experience these quantum packets in daily life.
You're spot on. It's tiny. The currently accepted exact key value of the Planck constant is H equals 6.626070015 times 10 to the minus 34 joule second.
10 to the minus 34, that's,
Yeah.
yes, staggeringly small.
It is.
Joule seconds, those are the units, right? What does that combination energy and time actually signify?
Physically. Exactly. The units are energy, joules times time seconds. And as we mentioned, this combination, joule-seconds, is also the unit of action.
Right, action.
Interestingly, it can also be expressed as momentum multiplied by distance. Kilogram meter squared per second.
Ah, so it connects momentum in space, too.
It does. It reveals these deep connections between energy, time, momentum, and space at the quantum level. It's like a thread weaving through all of them.
That's quite a fundamental thread. And I also recall hearing about a major overhaul of the international system of units. How does H fit into how we define things like the kilogram now?
Yes, that was huge. In 2019, a landmark decision, the SI base units were redefined. So now the Planck constant isn't something we measure with, ever-increasing precision. Instead, it's defined.
Defined, you mean fixed?
Fixed, exactly. It's defined to have that exact value we just mentioned, H 6.626070015 on a 10 or joule seconds, period.
Wow.
And this exact value, along with the defined speed of light, is now used to define the kilogram.
That's truly mind-bending. So a constant that started as kind of a theoretical fix now underpins our very definition of mass.
Isn't that amazing? From a radiation problem to defining the kilogram.
Incredible. Okay, I've also come across something called the reduced Planck constant, H with a little bar over it. What's the difference there?
H bar. It's simply the Planck constant divided by 2. So H2.
Okay, why divide by 2?
Well, that factor of 2 pops up all the time in quantum mechanical equations, especially when you're dealing with circles, oscillations, angular frequency.
Oh, right.
So using HR just simplifies many of those equations, makes them look cleaner. It's more about mathematical convenience in certain contexts than a fundamentally different concept.
So it's like using radians instead of degrees sometimes, just makes the math tidier.
That's a great analogy, exactly like that. Its approximate value is a 1.0545711817. Still tiny? And just as we have E, we can also write the energy-frequency relation using h bar and angular frequency as Edo, where O is just 2 times the regular frequency.
Got it. So H is the fundamental unit of action. H bar is a handy scaled-down version for certain calculations, usually involving angles or rotation.
You got it.
Okay, now that we've got the basics down, let's dive into what makes this tiny constant so incredibly significant. We touched on quantization, but can you give us some more concrete examples, the mind-blowing implications?
Absolutely. The fact that energy, angular momentum, and other properties in bound systems are quantized.
Meaning they come in steps.
Exactly. They can only exist in specific discrete amounts, like individual steps on a staircase, not a smooth ramp. That's a direct and profound consequence of H.
Okay.
At the atomic level, for instance, electrons orbiting a nucleus can only occupy specific energy levels.
They can't just be anywhere.
Nope. They can't exist in between those levels. And the difference in energy between these allowed levels is directly related to H.
That makes perfect sense. And this quantization is absolutely crucial for the stability of atoms, right? Otherwise, things would just collapse.
Precisely. If electrons could have any energy, they could just lose energy continuously by radiating and spiral right into the nucleus. Boom.
No more atoms.
No more atoms. No more matter as we know it. The quantization of energy levels dictated by H prevents this collapse. It's what keeps everything stable.
Wow.
But perhaps one of the most conceptually revolutionary implications of H is its central role in wave-particle duality.
Ah, yes, wave-particle duality, the big one. The seemingly paradoxical idea that light and even matter can behave like both a wave and a particle. How does tiny H act as the bridge here?
Well, as we discussed with E, the Planck constant directly links the particle-like property of light, the energy E of a single photon, to its wave-like property, that's frequency. Einstein's work on the photoelectric effect, that was huge.
All right, that won him the Nobel Prize, not relativity.
That's right. It provided compelling evidence for the photon, this discrete packet of light energy, and the amount of energy in each photon, determined by its frequency through HE.
So H is like the conversion rate.
Yeah.
Between the waviness of light and its particleness.
That's a great way to think about it. The conversion rate, exactly.
Okay.
And this duality wasn't just a quirky feature of light. In the 1920s, Louis de Broglie, he took this already mind-bending idea a step further.
Even further?
Oh, yes. With an even more revolutionary proposal that matter particles, like electrons, should also exhibit wave-like properties.
Wait, electrons? Like tiny little balls, they have wave properties.
That was the idea. He proposed that the wavelength of a particle is inversely proportional to its momentum and the constant connecting them.
Let me guess.
You got it.
BOP. So not only does light, which we think of as a wave, have particle properties like momentum,
Right.
but matter, which we think of as solid particles, has wave properties like wavelength.
Yeah.
And tiny h connects them both ways.
Both ways. For both light and matter. It's, yeah, truly astonishing.
It makes you wonder why we don't see the wave nature of, I don't know, a bowling ball rolling down the lane.
That's a crucial insight. The value of h, remember, is incredibly small, 10 to the minus 34.
Right, ridiculously tiny.
For macroscopic objects like a bowling ball, its momentum mass times velocity is enormous in comparison. So its de Broglie wavelength, ELEBA, becomes so infinitesimally tiny.
Too small to see.
Way too small, far beyond anything we could ever hope to observe. But for very small particles with tiny masses, like electrons,
Their momentum is small too.
correspondingly small, and their associated wavelength becomes significant enough to be measurable. It leads to observable wave-like effects like diffraction.
Which perfectly segues into another cornerstone of quantum mechanics where AH, or maybe H-bar, plays a starring role. Heisenberg's uncertainty principle.
Precisely. Good connection. The uncertainty principle, formulated by Werner Heisenberg, it states there are fundamental limits. You can't know certain pairs of properties perfectly at the same time.
Like position and momentum.
Exactly. The more precisely you determine a particle's position, we call the uncertainty ax, the less precisely you can know its momentum at that same instant and vice versa.
There's a trade-off.
A fundamental trade-off. Mathematically, this limit is expressed as x times ep is greater than or equal to h2. H bar over 2.
H bar again.
H bar again. And similarly, there's an uncertainty between energy and the time interval over which you measure it. H times it is also greater than or equal to h.
And the fact that h appears in these fundamental rules tells us that it's at this incredibly small quantum scale where these uncertainties really kick in.
Exactly right.
In our everyday big world, these uncertainties are so minuscule, we just never notice them.
Never. The smallness of ETS dictates the scale where quantum weirdness, including uncertainty, becomes relevant. And it's not just about our measurement tools being clumsy.
No.
No, it's a fundamental property of the universe at that level, baked into the system.
Wow. Okay, we also touched on atomic structure earlier.
Yeah.
Beyond just the quantization of energy levels, how else does H shape the atom?
Well, the quantization governed by H, or really H, extends to other key properties, most notably the angular momentum of electrons.
Angular momentum, like how they spin or orbit?
Kind of, yeah. In the early Bohr model of the atom, for example, which wasn't perfect, but a key step, it was postulated that the angular momentum of an electron orbiting the nucleus could only take on specific discrete values. Integer multiples of it.
Multiples of H bar.
Again, this quantization of angular momentum is absolutely critical for explaining the discrete spectra of light that atoms emit or absorb.
The specific colors.
The specific colors. Each specific wavelength, each color, corresponds to an electron making a transition, a jump between those allowed quantized energy levels.
So the unique fingerprints of light from different elements, those characteristic spectral lines we see, they're fundamentally tied to the Planck constant.
Absolutely. Those spectral lines are a direct consequence of the quantized energy levels and the precise energy differences between those levels, which are dictated in part by H, determine the frequency, and thus the color, of the photons emitted or absorbed when electrons jump.
Amazing.
And finally, we can't forget that the Planck constant, usually as at, is a central and indispensable component of the Schrödinger equation.
The big one. The master equation of quantum mechanics.
Pretty much, yeah. It describes how the quantum state of a system evolves over time, and H is right there in its core structure. You can't write it down without it.
It really does seem like this one incredibly tiny constant is the linchpin. It's holding together so much of our understanding of this bizarre quantum world.
It really is.
Now, let's delve even further into this wave-particle duality concept with H as our key. We've discussed it for light and matter separately, but how do these two sides of the quantum coin really fit together?
Right. So wave-particle duality, at its heart, is this realization. At the fundamental level, things don't behave exclusively as waves or particles like we're used to.
They can be both, depending on how you look.
Exactly. They exhibit both sets of characteristics, and which aspect we observe depends entirely on the experiment we set up. For light, remember, we had a very successful classical wave theory, Maxwell's equations.
Right, explaining interference, diffraction.
Yeah, Young's double-slit experiment.
Yeah.
Classic wave behavior. Light interfering with itself. unequivocal evidence that light could act like a wave.
So the wave idea for light was solid. What forced the particle idea back in?
Well, the wave theory just couldn't explain certain things. We mentioned blackbody radiation.
And the photoelectric effect.
And the photoelectric effect. Planck's quantization and Einstein's photon idea were needed. The photoelectric effect especially showed that the energy of electrons kicked out of metal by light depended only on the light's frequency, not its brightness.
Right, higher frequency, more energetic electrons. Brighter light just meant more electrons, but not more energetic ones.
Precisely. And there was that threshold frequency. Below it, nothing happened, no matter how bright the light. That screams packets of energy, photons.
And it's that fundamental equation, E phi, that serves as the crucial link, connecting the particle energy, E, to the wave frequency.
Exactly. It's the quantitative bridge, the conversion factor, as you said earlier.
Okay. Now, for matter, the classical view was simple. Particles are particles, localized things. Mass, position, momentum.
Straightforward. Then came de Broglie. His hypothesis was the counterintuitive leap, suggesting these particles also have an associated wavelength, given by EAP.
Linking momentum, particle thing, to wavelength, wave thing via H.
A truly symmetric and, well, elegant proposal. It mirrored what was happening with light.
And as we mentioned, we don't see baseballs diffracting because their wavelengths are just unbelievably tiny.
Right. EPP is huge for a baseball, so epicals is minuscule.
But for tiny electrons, it becomes measurable. The Davisson-Germer experiment was the key proof.
It was pivotal, yes. Davisson and Germer, they were actually studying how electrons scattered off nickel crystals, and they unexpectedly saw a diffraction pattern.
Diffraction, that's a wave thing.
Absolutely, a clear signature of wave behavior. And what was truly remarkable, the wavelength they calculated from that pattern matched de Broglie's prediction with astonishing accuracy.
Wow.
And shortly after, G.P. Thomson independently did similar experiments, passed electrons through thin metal foils, also saw diffraction rings.
So multiple confirmations.
Irrefutable evidence. Matter, just like light, exhibits wave-like properties.
It's just mind-boggling. Something solid, a particle, also acting like a spread-out wave, all governed by H. And it wasn't just electrons, right? Other particles, too.
Indeed. Since those early experiments, this wave nature has been confirmed for a whole zoo of particles. Neutrons, protons, entire atoms.
Atoms act like waves.
Yep. And even relatively large and complex molecules, things like buckyballs, C60 molecules. They've shown wave interference, too.
That's incredible. So wave-particle duality seems universal for everything quantum.
It appears to be a fundamental and universal property of all quantum entities, not just some weird quirk of light or electrons. It seems baked into the fabric of reality at that level.
So to bring it all full circle, it's clear the Planck constant isn't just some random number. It's absolutely fundamental to this whole bizarre but successful concept of wave-particle duality.
That's the core message, yeah. H is a fundamental ingredient in the math. The recipes that quantitatively connect particle properties, energy, momentum to wave properties, frequency, wavelength.
For both light and matter.
For both. And it dictates the scale at which these dual aspects become significant and observable.
So if H didn't exist, or had a wildly different value, we wouldn't have this framework. No way to understand how light and matter can be both waves and particles.
Precisely. Without eighth, those fundamental relationships, E high and eighth, they just wouldn't exist as they do. Our entire understanding of the quantum world.
Which underlies so much technology.
Everything. Lasers, transistors, semiconductors, modern medical imaging. It would all be fundamentally different, maybe impossible. H truly quantifies that inherent waviness of particle momentum and the inherent particleness of wave energy.
It's truly humbling to consider how this one minuscule constant orchestrates so much at the deepest level of reality. It really prompts you to wonder about other seemingly insignificant aspects of our universe. What other seemingly small or overlooked details might hold equally profound secrets just waiting to be uncovered? Perhaps contemplating the intricate interconnectedness of seemingly disparate phenomena? Maybe that's the next step, unlocking even deeper truths about the cosmos.
That's a wonderfully thought-provoking question and a perfect point to reflect on as we conclude. The Planck constant is a powerful reminder, isn't it? The universe often hides its biggest secrets in the smallest details.
Thanks so much for taking this deep dive into the Planck constant with us today.
My pleasure. Fascinating stuff.
Until our next exploration, keep pondering those fundamental questions.